we're going to finish looking at section 2.2. And we're going to look at a problem where we have a company that's going to produce a product, and the company is going to get a certain amount of money from the product they sell. We're going to call that revenue. But they also have to spend a certain amount of money to make their product. We're going to call that cost. But this particular company is going to have two kinds of costs, fixed and variable. The fixed cost never changes. The variable cost does change. It changes with how much product they produce. So in our case, the company has a fixed cost of $200,000. Maybe that's the cost to rent the building for the month. Cost them $200,000. They can do whatever they want in the facility. If they make one shirt, the cost to rent the building is $200,000. If they make 1 million shirts, still costs $200,000 to rent the building for the month. The variable cost is going to have to do with how many shirts they make. The more shirts they make, the more shirts they need to buy so they can print them, or whatever they're going to do. So it costs this company $1.50 for every shirt that they make. Maybe that includes the cost to use ink and print on the shirt, to buy the shirt from a company that makes shirts. But it costs them $1.50 per shirt, and they're going to sell the shirts for $4. So what I want to do is set up two equations, one that models the costs and one that models the revenue. Let's start, well, we'll find graphs after we do the costs and the revenue. Let's start with the costs. What's one thing that this company has to pay for? Yeah.
Shirts?
Yeah, they have to pay for shirts. How much do they pay per shirt?
Less than $1.50.
Can you give me an exact number that they pay per shirt?
Is it $1.50?
It's exactly. It's a variable cost of $1.50 per shirt. Each pyramid is. Since it's $1.50 per shirt, do we know how many shirts the company is going to make? That's my variable. So we need to pick a letter that represents the number of shirts. Let's not use S, because my S's look like 5s. So what would be a good letter to represent the number of shirts? Yeah?
N.
Sure. N for number of shirts. So I'm just going to put that, I'll put that right down here. N is the number of shirts. Okay. So it costs $1.50 times N. Plus there's another cost. What's the other cost in the problem that doesn't change? Yep.
$200,000.
Plus the $200,000. Perfect. That is what the company spends. Okay. Now we want to figure out what's the money that the company receives. Not necessarily the profit. The profit is going to be the difference between the costs and the revenue. I just want to know what is the total, and I thought we were going to use X. I should really make that an N. What's the formula for the total amount of money that the company will receive per shirt? Yeah? $4, and what would be your formula right there? Yeah, we're going to use N. Okay. So that's the amount of money the company spends. That's the amount of money the company receives. And then you could see if they had profit by looking at the difference. Any questions how we came up with those two equations? All right, so now let's graph them and see what they look like. Okay, 1.5x plus 200,000 and 4x What's my y-intercept? on the y1 equation? Yep.
0, 200,000.
It's at 200,000, yeah, 0, 200,000. So we should probably set the y max even higher. I would probably do, let's try like 500,000. Give us a lot extra. Now, can we have a negative amount of revenue? Is it possible somehow to plug in a number of shirts here and get a negative answer in that box? No. Could you have a negative amount of cost if you plug in a number for n in that box? No. You could have a negative amount of profit when you look at the difference, but in and of themselves, each one of those formulas will give you positive numbers. So negatives, don't worry about those. X is the number of shirts we sell. Okay, we don't know how many shirts we're going to sell. Let's just say, this company's making lots of shirts. Let's say, I don't know, maybe they sold up to 50,000 shirts. If we need to see more, we can look at more shirts. Okay, but I'm just putting in a number so I can see it. Okay, so there's my revenue, there's my costs, and there's my revenue. What's happening if you look at that graph when you look at the costs and the revenue? Yeah?
At the on the left side of the graph, it costs more money to make the shirts than what they're selling, and as they start making more, the spending isn't going up as high.
Yes, and so as they start selling more shirts, their revenue is catching up to their cost, meaning eventually they're going to start making money. Up to 50,000 shirts, they have not made money yet. It still has cost them more with the 200,000 plus the cost per shirt. So maybe let's go a little higher. Let's say we go up to 100,000 shirts. Yeah, I think we're going to be good now. Where on that graph do they start making money? Not the number, but just describe to me where. Yeah?
Past the intersection.
Yeah. If you look at the intersection point, that particular point has a name, and that's called the break-even point. The break-even point is when your cost graph and your revenue graph are equal. And when you're looking at a graph, that's the intersection point. So what we're going to do is we're going to use our graph, figure out the intersection point, and then we'll figure out the break-even point by calculating the intercept. So we'll do it as a graph, and then we'll do it algebraically. But let's do the graph first. Can someone remind me? We just did this in the homework. What are the buttons I press to see where the break-even point is? Yeah, Aiden.
Second calc 5, and just enter 3 times.
Yeah, we just hit enter 3 times because there's nothing we need to adjust. Okay. And I don't know how well you can see it, but it says x equals 80,000. What is that 80,000? It's telling me, yep.
It's the amount of shirts you have to sell before you break even.
Right. It's the amount of shirts that I need to sell before I break even. If I sell 80,000 shirts, what will my costs be? Looking at that graph. Yeah.
320,000.
My costs will be 320,000. If I sell 80,000 shirts, what will my revenue be? Yeah. Yeah. Revenue is the money that the company takes in, not necessarily their profit. So if I sell 80,000 shirts, my cost is 320,000, and the revenue is, it's also 320,000. The cost and the revenue are the same. The profit is 0. Okay. So that's how you solve it graphically. Graph each one. You've got to make sure the intersection point is on the screen when you set your window. Now, let's do the same thing So we've already done it graphically. Let's do the same problem again, but algebraically. So remember, algebraically is where cost is the same as revenue. Cost is the same as revenue. Okay, what was my formula for cost from the previous page? Yeah, Kelsey?
Is it 1.5n plus 200,000?
1.5, yeah, and I had this set up for x, we decided to use n, that's fine. So 1.5n plus 200,000. What was my formula for revenue? Yeah,
4n.
Charles? 4n. Now just solve it and see what you get. So bring the 1.5 to the other side. And my last step, divide by 2.5. So 200,000 divided by 2.5, 80,000. So that's how you can solve a break-even point algebraically. Set the cost equal to the revenue. And graphically, I already did that. That's where you do the intersection point. And I think that was it for that section. Does anyone have any questions on how we got the break-even point? Okay. So there'll be, I think, 4 of the questions tonight are from that section, and they're all related to the same thing. Write the cost, write the revenue, show a graph, calculate the intercept. That'll be 4 questions, all related to a break-even point problem. All right, so the last thing we're going to look at, and we'll spend most of today on this, is solving equations, both linear and quadratic. So remember that for something to be an equation, it has to have an equal sign. This is not an equation. So if somebody wrote 2x plus 3 and said solve, you can't do that. You need to know what it equals. It has to be an equation. If your particular equation, let's say it looks like this, has the letter x in it, then we can say that's an equation in x. Excuse me. It just means that the letter that you're using is x. I usually say it that way. My equation uses the letter x. But you might see that wording in the book. So when I think the wording in the book could be a little different than what you're used to, I try to mention it. So you might understand what they're talking about. So when I ask you to solve an equation, that means I want you to find the value that makes it true. Some equations will have more than one answer. Some equations could have no solution. In general, though, a linear equation can have at most how many answers? When you're solving a linear equation. At most. Natalie? Yeah, at most it could have 1. A quadratic could have at most, yeah, 2. Could have 1, could have none that are real. And for now, we're only talking about real numbers. But yeah. So some equations are what we call an identity. If something is an identity, then that means it is true for all values. You might wonder, how could any number work in an equation? Well, you could have something like that. That's an identity. Why is that equation an identity? I think, yeah.
When you simplify the right side, it comes out the same as the left.
Yep. When you simplify the right, it's exactly the same as what's on the left. And because you have the same thing on both sides, no matter what you plug in for x, it will always work. Now, if you compare that to a conditional equation, that's an equation that is true if you pick the right number. It's not like an identity where you could pick any number. You have to pick the right number. So in this case, if you plug in 5 for x, that's the condition that would make this equation true. I think we already talked about those. Like the first day, talked about different kinds of equations. So any question on the difference between an identity and a conditional equation? Okay. So sometimes what I might ask you to do is, once you solve something, is to check your answer. To check your answer or verify that what you found is the right answer. You take your answer, you plug it back into the original problem, and you see if you get a true statement. So with something like a cubic, we might not know how to solve that yet. I'm telling you that -2 is an answer. I just want you to check it. Later in the year, you're going to know how to get that -2. But for now, I just want you to check that it works. So Stephen, how do I check that -2 is a solution?
Plug it into x.
Yeah, which x?
Both of them.
Both of them, yep. Plug it back in for x. And I'm going to put a question mark there because that's what we don't know. We're trying to see, if I plug in -2, do I get 0? Let's check. Asher, what's -2 cubed? So we get -8 minus -2 becomes +2. And Jaden, what's -8 plus 2?
-6.
And then +6?
0.
0. Okay, so I plugged it back in. Did I end up with a true statement when I plugged it back in? Yeah. Since I got a true statement, that proves -2 is a solution. Not saying the only solution, but it is a solution. If you plug it back in and you do all the arithmetic right, and you end up with like 0 equals 5, what would that mean? Yeah.
Not a true solution.
Yeah, it means it's not a solution. The number that you found doesn't work, assuming you did your arithmetic right when you checked it. Okay, so any question on how to verify if a number is a solution? Okay. So let's start with linear equations, and then we'll move to quadratics. So in our book, that is the definition of a linear equation. It's of the form ax plus b equals 0. Or it could be rewritten to be in that form. A and b can be any real numbers you want. But in our book, to be linear, it says it has to have the x variable. If you made a 0, and you put in 0 times x, what is 0 times x? 0. It would effectively wipe out that first term, and you wouldn't have it anymore. Okay? And that would not be linear, according to the definition in the book. Okay? But other than that, a and b can be any other real numbers that you want. Now, that's an example of a linear equation. It doesn't look like ax plus b equals 0. It could look that way if we wanted to. But the goal is to solve it. And remember, we get at most one answer. first step. Emma, what would be my first step to solving this equation? Yeah, and can you tell me what you get when you distribute all that out? Mm-hmm. 4x. Okay. Perfect. All right, so we got that. Sunny, what would be my next step?
And then you would combine like terms.
Yeah, we got some like terms on that left side we can combine. Can you go ahead and do that for me?
Sure. You end up with 7x minus 3
All right.
times 5x plus 2.
So we combine like terms. Charles, my next step?
Isolate the variable.
Okay, so you gotta get the variable on one side. How would you do that?
You can add 3 to both sides.
All right, so we can add the 3. And what else could we do at the same time?
Subtract 5.
Yep.
X.
Subtract 5x. Okay, that leaves me with 2x equals 5. So x equals 5 halves. Okay, so that's solving a linear equation. Okay, at this point in pre-cal, you should be really comfortable solving equations like that. Questions on that? So an application of solving linear equations is an absolute value problem. What's going to happen in an absolute value problem is it's going to split into 2 linear equations. So let's say you had something like that. That's an absolute value equation. I'm not going to do that one. But when you are solving an absolute value equation, you need to make sure that the absolute value expression is isolated on one side. In the problem I just wrote down, it is isolated. Here's an example where it's not isolated. 2 plus the absolute value of 3x plus 2 equals 4. Now you've got a 2 plus on the outside. Does anyone have a guess what you would need to do with that to get it on the other side? Yeah?
Subtract 2.
Yeah, you'd subtract 2 and subtract 2. That's gone. And now you have the absolute value of 3x plus 2 equals 2. Sometimes you have to do that, sometimes you don't. All right, but that's the first step. Isolate the absolute value expression. Now we're going to split it into 2 problems. Okay, and I'll make one up right here. Just to show you how it splits up. Once you get the absolute value by itself, you're going to split it into 2 problems. The first one, you just take out the bars. 2x minus 7 equals 5. So you just copy the equation without the bars. The second one, you're going to copy the equation without the bars again, but you're going to make the number on the other side the opposite. Okay? That's what that means. Change the sign of the number on the other side. So in this case, 2x minus 7 equals negative 5, and now you solve it. And the reason you do that is because you're looking for something right here that has an absolute value of 5. What 2 numbers have an absolute value of 5? 5 and negative 5. So if you set what's inside here equal to 5, and then take the absolute value, you'll get 5. If you set what's inside there equal to negative 5, and take the absolute value, you also get 5. Okay, but that's kind of the main idea of how you solve absolute value equations. So let's try this one. So it's the absolute value of 2x plus 3 equals 5. Okay, first thing. Is the absolute value by itself on one side? What do you think, Elise? Yeah, it's by itself, so we're ready to split this into two problems. Anybody think they can give me the first equation that this is going to split up into, and this is going to get rid of the butters? Yep.
2x plus 3 equals 5.
So we get either what's inside there can come out to 5, or what's inside here can come out to
X plus 3 equals
negative 5. At this step, now we have two linear equations to solve. So we get 2x equals 2, x equals 1, 2x equals negative 8, x equals negative 4. And that's it. They're both answers. So you've got to make sure when you're solving absolute value that you write both answers, because if you write one, usually there are two. So always solve for two. All right, what if you had a problem like this? So you might say, okay, absolute value is by itself. I'm going to split it up and start solving it. But look carefully at that. Yeah?
no solution because the solution can't be negative.
Yeah, I don't care what you take the absolute value of, it's never going to equal negative 5. So that is a no solution. You can't solve that one. Now, when you look at that one, it's no solution. But let's say you had something like this. Negative 12 plus the absolute value of 3x minus 4 equals negative 5. You might look at it quick and say, oh, absolute value equal to a negative, no solution. But this time there is a solution. How come? Why is this different, Matt?
Because when you add the 12 to both sides, cancel it out and it's positive.
Right. When you add the 12 to both sides to get that absolute value alone, you're going to end up with a positive 7 on that side. So in this case, when you isolate it, it becomes positive. And then you can solve from there. Any question on that? Okay. So last thing we're going to do for linear, and then we'll finish up with quadratics, is a mixture problem. A mixture problem requires a system. Okay, that means you're going to have to set up two equations with two letters. Generally, what we're going to have in this kind of problem, like as an example, let's say you had two different bottles of rubbing alcohol. The first one was 70%, the other one was 90%. Okay, so two bottles, 70%, 90%. I want to mix the two together to create an 83% solution. And when I'm done, I need 10 gallons of it. So I want to know how much 90% and how much 70% should you mix together to make exactly 10 gallons, and it has to be 83%. All right, so you're going to have to set up two equations to do that. The first equation would represent, for example, the amount of 70% rubbing alcohol plus the amount of 90%, and that equals the total amount. I think I said 10 gallons. Okay, so you'll always be given the total amount. What you won't be given is amount 1 and amount 2. Those have to be variables. Okay. Everything I'm highlighting is going to be a variable. That equation doesn't take into account anything with percentages. It's just the amounts. The next equation is going to take into account the percentage strength or concentration of your mixture. Yep. Yeah, just sign off. So the next equation is the concentration times the amount. So if this was like the 70%, the concentration is 0.7. You have to make the concentration, just like we did yesterday with the interest, you gotta make it a decimal. So 0.7 times some amount. The other concentration will be given to you. I think I said 90%. So it would be like 0.9 times some amount, which you don't know. And then the final concentration and the final amount, those are also both given. So in the problem I made up, I think I said I wanted a concentration of 83%. So that'd be like 0.83. And the total, I said 10 gallons. So that'd be a 10. So everything that's not highlighted in yellow will be an exact number. The other two things that are not, the other four things highlighted in yellow, those will be variables. Same variables in each equation. So let's see about that. If we can set this up. Okay, so we have two different solutions. In our case, it's a 10% and a 25%, but they're always percents. Okay, just to keep it clear what we're talking about, I'm calling them solutions A and solution B. And let's use A and B as the amounts. Okay. Let's say we're going to use A liters of solution A, and we're going to use B liters of solution B. This is my amount 1 and my amount 2, A and the B. So you have everything you need now, except what do they want you to create? Well, how much liquid do they want? What's the percentage that they want? The percentage has to be between 25 and 10. There's no way you could create a concentration here of like 30%, because you don't have one strong enough to do that. So it's got to be between 10 and 25. But any question how A is amount 1 and B is amount 2? You could use X and Y. I just figured it's easier to remember which one is which if we use the name of the solution. Solution A, solution B. So they want us to mix it together to create 15 liters, and the strength of it has to be 12%, which is doable because it's in between 10 and 25. Because it's 12%, you're probably going to use a lot more of solution A than you are of solution B. It's like you're just going to pour a little bit of B in to make it stronger. Okay, so that's my final concentration, and that's my total. All right, let's see if we can set up those two equations. Amount 1 plus amount 2 equals total. Anyone think they could give me that equation? Amount 1 plus amount 2 equals total.
A plus B equals 15.
Yep. A plus B equals 15. Perfect. There's one. Now the second one, concentration times amount 1. Well, let's start there. What's the concentration of my first solution as a decimal? 0.1 times the amount of that solution. How much of that solution are we using? A. Yep. Plus concentration times amount again. What's the concentration of the second solution? Yep. 0.25 times B equals the final concentration times the total. What's the final concentration of the mixture? 0.12, and times the total is, what's the total? Yep. 15. We can clean that second equation up a little bit. Let's just say 0.1a plus 0.25b. I think 0.2 times 15 was 1.8. Somebody can double check me on that, but it's, yeah, from the last class. I just remember doing it. Okay, there's your system. 2 equations, 2 letters. Does anybody remember how you can solve a system? And I would do something to this one and then take that and put it somewhere else. Yep.
So if you isolate one of the variables in the first one,
Okay.
plug it into whatever variable you're going to isolate to in the second.
Yeah. So could you tell me a variable you want to isolate in the first one?
B,
B. Okay. What would B equal?
15 minus A.
Yeah, 15 minus A. Now, you said to take that and plug it where?
Into B.
Into B. And the name of that method is substitution. Yep. Not the only way to solve a system, but this one I would use substitution. 0.1a plus 0.25, we're not going to write b anymore. We're going to write 15 minus a. 1.8. Okay, so we're going to distribute. Can somebody tell me what's 0.25 times 15? What is it, 3.75? Okay. So we get 0.25 times 15 is 3.75. 0.25 times negative a equals 1.8. Combine your like terms. You've got 0.1. Take away 0.25. That's negative 0.15. And we need to bring the 3.75 to the other side. What's 1.8 minus 3.75?
Negative 1.95.
Negative 1 point what?
95.
Negative 1.95. And it's good that I have negatives on both sides, so those cancel, because I would not want to get a negative amount for my answer. What's 1.95 divided by 0.15? Is that 13? 13? Okay. So that means we need 13 liters of solution A. And using your formula that you substituted for, you can easily figure out B, because now you know this is 13. So how many liters of solution B? 8? 2. Yep. Okay, it's a little more advanced application for linear equations, but still just linear. Any question on solving that system? That's pretty much, that's all your work right there. All right, so the last type of problem we'll look at is quadratic. So quadratics have an exponent of 2 as the highest exponent in the polynomial. The a, the b, and the c are the number in front of x squared, the number in front of x, and the constant, respectively. A, b, and c can be any numbers that you want, except a can't be 0. What would happen if you plugged in a 0 for the a? Yeah.
It would get rid of the x squared and make it linear.
Right, we'd get rid of the x squared, and all you'd have is bx plus c, which is now linear. The highest exponent would be a 1. So one method to solve the quadratic equation, you learn this method if the numbers work out nicely. Does anybody know the method I'm thinking of to solve a quadratic if the numbers are nice? Yep. Factoring. Yep. So this isn't really a full lesson on how to factor. That's kind of a Algebra 1 skill. So factoring is important. We'll do one just to kind of refresh you a little bit. But factoring is something I probably spend a few days on, in algebra. Okay. So what's the first thing when you're going to factor that? What's the very first thing you want to write down? It doesn't even have anything to do with numbers or letters. But you do this anytime you're going to factor. Yeah? Yeah, you need to just put 2 sets of parentheses. Okay, first thing. We need 2 things that multiply together to give me 2x to the second power. What would be 2 things that multiply to give me 2x to the second power?
2x.
Yep, perfect. And there's no other choice because 2 is a prime number. It's not like 12x squared. If that was 12, well then you get 6 and 2, 3 and 4. You got lots of things to try. Okay, next thing is we need our signs. We have a positive middle and a negative constant, plus and a minus. What does that mean my signs are going to be in the factor? Yeah?
2 negatives.
Well, if they were 2 negatives, then when you multiply negative times a negative, you'd get a positive right there. So it can't be 2 negatives. Yeah?
Positive and a negative.
It does have to be a positive and a negative. And it makes a difference which one we put where. If you're not sure, well, you can guess. But I would suggest negative, positive. If they're wrong, you switch them. And now we need 2 numbers that multiply to give me a 3. And again, 3 is prime. So what can we multiply to get 3?
1 and 3.
1 and 3. And I would do them in that order. Let's check it. 2x squared. 2x times 3 is 6x. Negative 1 times x is negative x. And 6x, take away 1x, 5x. Perfect. All right. Now, this is kind of like when we saw in the homework. You've got something times something equals 0. What's the only way you can multiply 2 things together and get 0? Yeah.
If one of the sets of parentheses equals 0.
Right. One of those sets of parentheses has to equal 0. Either this one or this one. Now that you've factored it, you've basically taken it from a quadratic and turned it into 2 linear equations. Kind of like with absolute value, but sometimes the linear equations are a little harder to come up with because you got to know how to factor. Okay, so here we get x equals, yeah, 1/2. And the second answer, x equals, yeah,
Negative 3.
-3. Okay, so if it factors, great. What if it doesn't factor? What's another method we can use to solve a quadratic besides factoring? Yeah.
Quadratic equation.
Yeah, we can use the quadratic equation. So if you don't remember the quadratic equation, probably a good idea to write that down. So this formula relies on using the A, the B, and the C. And remember, I pointed out what those 3 things were. A is the number in front of x squared. B is in front of x. C is your constant. So you've got to get the equation equal to 0. Really, whether you're factoring or using quadratic formula, you always want it equal to 0 for those 2 methods. Does everyone have the formula? Let's try this one. So 2x squared plus 2x equals 1. Is that in standard form? Yeah. No, not in standard form. John, what do I have to do to get that into standard form?
Subtract 1.
Yep, subtract 1 on both sides. Make sure we know what letter is what. Okay. Madison, what's A in this case? 2? Jordan, what's B? Yep, it's also 2. And C, Nolan, what's C?
Negative 1.
Negative 1. Okay, so now it's just a matter of filling those into the formula and seeing what we get. When the directions say solve, the expectation is you're going to leave your answer exact. Okay, don't round it to decimals unless they specifically say round your answer to 2 decimals. I would always clarify that on a test if you weren't sure. So negative b plus or minus b squared 4ac over 2a. We'll just double check that. Now, we're going to be subtracting a negative number. So subtracting a negative turns into what? Turns into positive. So might as well just do that right now. And what's 4 times 2 times 1? 8 plus 4. Well, Everett, what does that give me under the radical? 12. Okay, and how can we reduce the square root of 12? What would that turn into? So we did this when we did the distance formula, I think. Yeah.
2 square root of 3.
That would be 2 square roots of 3. And now, everything that's outside of the radical is divisible by what? 2. So yeah, we need to divide everything by 2 to reduce that as much as we can. So negative 1 plus or minus root 3 over 2. And that's your final answer. They didn't say to round it, so I'm not going to worry about any kind of decimals. And that's the other method that you can use to solve a quadratic when it doesn't factor. Because of the answers that I got here, I can tell you that this is not going to factor with nice numbers. I mean, technically, everything is factorable. It's just, you're not going to be able to factor something if it would be x minus 3 square roots of 2 over 6 and x plus 3 square roots of 2. Like you're not going to be able to guess that when you're factoring. Factoring only works really when it's integers. We could work with it in our head. Any questions on that? Okay. Okay, so we already did one where it wasn't equal to 0. That was the last question. Okay. So it's a good stopping point. That finishes up 2.3. So page 88. 33 to 39, that's a break-even point. 35 to 39, sorry, 35 to 39. It's a break-even point problem. So it's all the same question. And then the page 96 focuses on solving linear and quadratic equations. Reminder, I will be after school tomorrow. Test will be on Thursday. We have half a period on Friday. So we could take some time to review on Thursday before the test. And then you'll have time to finish the test on Friday if you need. There won't be any homework on Thursday night because you have the test. And there also won't be any homework on Friday night because we're finishing the test.